We finished chapter 3 with a discussion that's going to carry us through the rest of this entire year. That's antiderivatives. We've been talking about derivatives so far all semester. And the antiderivative, as the name implies, does exactly the opposite thing. Now it says here that capital F is the antiderivative of lowercase f if lowercase f is the derivative of capital F. So f is the antiderivative of little f as long as little f is the derivative of capital F. All right. So oftentimes it's easier to answer a question, what's the antiderivative of cosine, for example? What's the antiderivative of cosine? Well, another way to ask that question is, cosine is the derivative of what? And if you say it is the derivative of the sine of x, you are correct. So that makes sine of x the antiderivative of cosine. Now the instructions here say find the most general antiderivative. And what that means is, sure, sine is the antiderivative of cosine, but could there be some constant involved as well, like a 5, sine of x plus 5? If I take the derivative of that, would I still get cosine of x? And the answer is yes. And so just keep in mind, when you're asked for the general antiderivative, to include this plus c is going to be important, because there may or there may not be some constant involved. And we'll see its usefulness in just a little bit. Now for part B, finding the antiderivative of x to the n. When we found the derivative of x to the n, and I'll just do that up here, we brought the exponent around front, and then we decreased the exponent by 1. So now we're doing antiderivative, we got to do the opposite. And so what we're going to do is we're going to take, and I'll call this capital F of x. We're going to take that exponent, and instead of making it one smaller for the derivative, we make it one larger. Instead of multiplying, we will divide by that new exponent. And then add c because we're asked for the most general. So increase the exponent by 1 and then divide by that new exponent. Another thing to keep in mind is that just as it did with derivatives, any coefficients will always still come along for the ride. Okay, let's try letter B on letter C here. Let's bump this exponent up by 1. Then divide by the new exponent. Now, I think you can see we're not going to leave our answer like that. Instead of dividing by a third, we could multiply by the reciprocal. Instead of having a negative exponent, we could bump that down to the bottom. And then remember to add c. Now this one's a little bit different. This one, boy, you think of that and you think of, well, I could call it x to the negative 1. So I'm going to bump that exponent up by 1. Whoops. And then divide by that new exponent. And I think we can see that's a problem. When you're dealing with 1 over x, best to ask yourself the question, 1 over x is the derivative of what? And if you said that 1 over x is the derivative of natural log of x, you are absolutely correct. Now, one thing that kind of messes people up is, what if we had 5 over x? Well, isn't that 5 times 1 over x? Isn't that 5 a coefficient? Don't coefficients come along for the ride? And we get 5 natural logs of x plus c. So don't let that constant throw you off. Just 5 times bigger than it used to be. Letter E, -8. What's the antiderivative? Well, -8 is the derivative of -8x, because the derivative of -8x, -8. Now, letter F looks more complicated. Letter X might make you hope that there's a quotient rule for antiderivatives or something. But there is not, and I should finish this root symbol here. This goes back to best practice of simplifying before we try to take a derivative or an antiderivative. If we have 2x over, well, now the square root of 4 is a 2. And the square root of x is x to the half. So I'm going to rewrite it. I'm going to simplify it. And now, just as we did up here in letter B and C, we're just going to take that exponent, we're going to bump it up by 1, x to the 3/2, and then temporarily I'm going to divide by 3/2, but realizing we never divide by a fraction. Instead of dividing by 3/2, I would multiply by its reciprocal of 2/3. Really drew that poorly. Almost forgot. So, this is the derivative of what? Well, it's the derivative of the antiderivative. Okay? Now, see how this all comes into play. F double primed of x we are given right here. And we're given some information about the first derivative and the function itself. And we are asked to find what that specific function is. What is the specific function that has this as its second derivative and also has these specific values along the way? Well, the first thing I would do is find the antiderivative of f double prime, and that would be f prime. And I'll take the antiderivative of each individual term. -2 has the antiderivative of -2x. 12, come along for the ride. X, you must become an x squared, and I got to divide by 2. I'll clean that up shortly. 12, come along for the ride. X to the and then plus c. Well, cleaning these things up, I think I'm going to replace this 12 over 2 with a 6. and the 12 over 3 are going to get replaced with a 4. And we're probably going to do that stuff in our heads and just write the 6 and write the 4 the first time. But seeing it done this way just reiterates that that coefficient comes along for the ride. Now, here's what I know. I know that f primed of 0 is 12. If I put a 0 in place of my x's, I'm going to get a result of 12. And that helps us figure out what c's got to be. C is going to have to be 12 because the rest of these terms all result in 0. So I got a 12 here. And I've got f prime. Now let's work our way again. Ultimate goal, figure out what f is. Antiderivative of negative 2x. Negative 2. X squared over 2. Clean it up. Plus 6. X cubed over 3. Again, a lot of people just doing that in their heads, writing the 2 immediately. 4. X to the 4th over 4. Plus 12x. And then, in general, we have a constant. However, we're not talking in general, we're talking specific. We know f of 0 is equal to 4. So I'll replace this with a 1. Or by not writing anything. Let's just keep in mind, let me make that negative sign a little bit bigger. This guy's becoming a 2. This is 1x to the 4th, 12x. And now when we replace all of these x's with zeros, we get a result of 4, meaning that the constant is going to have to be a 4. And that is the specific value of f of x. That is the specific function that has these properties and this as its second derivative. All right, one more. Now, what's written in red here is not given on your slide, so make sure you write that down. When we're talking about things being measured in meters and time being measured in seconds, the acceleration that gravity causes is constant, and that acceleration is negative 9.8 meters per second squared. So that's a constant, A of t, negative 9.8 in this problem. We're dropping this stone from a 433 meter high cliff. And that is acceleration. We would like, in part A position function. So in part A, I'll start out by saying that A of t is negative 9.8, which means that its antiderivative, velocity, is negative 9.8 t, we're not dealing with x's here, we're dealing with t's, plus c. Now, much like the last problem, are we given any velocity information? Back here, we were given some first derivative information, and that allowed us to find the value of that constant. Are we given any velocity information that will help us find the value of this constant? And it doesn't jump right out at you. But since the stone is dropped, when you drop something that moment your hand leaves it, what is its velocity? At a time of 0, I know that we get 0 as our velocity. Just momentarily, start speeding up quickly, but momentarily, we're getting a velocity of 0 at a time of 0, and that's what dropped tells us. And so if I put a 0 in for t and my result is 0, that means c is 0. So it was there, but I know it's got a value of 0, so I'm going to keep this as less complicated as I can. Now our goal here in part A is to figure out what is the height function. So the height at any time, oftentimes position is s of t. We could have called it h of t, wouldn't have mattered. Negative 9.8. P squared over 2 plus c. And I would probably replace negative 9.8 over 2, negative 4.9. Are we given any position information? Well, I think we are given position information that if the position at a time of 0 is 433, we are 33 above the bottom of the cliff, meaning that our constant is going to have to be 433. So we got to pick through these problems and the information that we're given in order to find any initial velocities or initial positions. So part A is complete. This is the position at any time. Part B. How long will it take to reach the ground? Well, what do we know about this thing when it hits the ground? I think we know that the position at that time, whatever that time is, the position is 0. So we've got to take negative 4.9 t squared plus 433. We've got to set that equal to 0 and solve for t. So I'm going to press pause. I'd like you to press pause, see what we come up with. I'm thinking we came up with t equaling 9.400. Now there were some digits after that, but in an effort to use my calculator, answer part B, I only have to be accurate to 3 decimal places. Now if I ever have to use this number for something, I think I would probably have to use the rest of these decimal places. So let's keep those on our calculator and let's not hit clear, just in case we need that for part C, which says what is the stone's velocity when it hits the ground? Well, this is my velocity equation. The velocity at this 9.400, and there are more digits involved here, is going to be equal to negative 9.8 times that time value. But I got to use all of these digits so I can have this answer accurate to 3 decimal places. So let's multiply that and see what we get. I don't know that it would have made a difference with that 3rd decimal place or not, but I think the velocity with which it hits the ground is negative 92.123 if we truncate, or 124 if we round. And kind of set a poor example. in Part B should have included units. In this case, meters per second. Up here, this was in seconds. So this is a way that we can have a actual real-life application of these antiderivatives. We'll see this kind of problem on our assessments. We'll see this on the AP exam as well. So that is our introduction to antiderivatives.